We're going to move into chapter 4, which is going to be topics in number theory. We're going to be able to explain and understand those divisibility rules, factors and multiples, divisibility tests, and we're also going to look at sets of factors as finite and the set of multiples as an infinite group. It's going to be really important to take some really good notes here because you've probably seen these divisibility tests in the past, but a lot of the time it's just a matter of keeping all of the rules straight. So having a quick reference sheet is going to be the ideal situation to doing well in this module. So we define an integer as even if it has a remainder of 0 when it's divided by 2. If it's not even, then it is odd. So the requirements for an odd number are just that it fails the even test. So when we say that 3 divides 18, that would be 3 divided 18 because the remainder is 0 when 18 is divided by 3. So this would be similar to dividing some number by 2. And we're going to show it with this slash here, this vertical line, because it's very similar to a fraction when you turn it horizontally. And we're trying to kind of build that foundation right now. We would say that 3 does not divide into 25 evenly. It does not have a remainder of 0 when 25 is divided by 3. So this is just an example of remainders. This is not an example of finding an even or an odd number. It's just a review of remainders. So in general, some number A is an integer and B is a positive integer. If A is divisible by B, the remainder is 0. So when you're doing these things by hand, remember we're not doing calculator yet. When you're doing these things by hand, if it goes evenly into it, meaning there's no remainder, then it divides evenly into that number of groups. If we have somewhere where the remainder is not going to be 0, then there is going to be some number that may have a remainder where if I multiply them together, I'm going to get that number. But it might be something like 1.5 times 2 is 3. So 3 doesn't divide evenly by 2, but I can still say 1.5 times 2 is 3. So this is kind of a play on words. So I can still say if the remainder is not 0, I can still say that I have a factor or divisor of A and it's a multiple of some number B. So if you get a remainder, decimal remainder, that's what we're looking at here. So here are some examples. 3, classify them as true or false. Is 3 evenly divisible by 12? Yes. Is 0 even divisible by 2? No, false. Is 0 even? Remember, our definition of even is if we can divide it by 2 and there's no remainder. We can do 0 divided by 2, that's 0, and there's no remainder. So technically 0 is even. Is 8 not divisible by 2, or is 2 divisible by 8? That's going to be, it's true, it's not divisible because 8 is larger, it cannot go into 2. For all whole numbers, the number A divided by 1 is itself, which is true. If I have all whole numbers, can A to the 5th be divided by A squared? True. The top exponent has to be smaller. 3 can go into 6n for all integers of n. Yes. So if it's 6 times 1, 3 can go into 6. If it's 6 times 2, 3 can go into 12. So that's always going to be true. Then this one says, is this not going to be divisible? But I have to work with what's inside of these parentheses. So I have to figure out what is 5 times 7 times 9 plus 11. Then take that number and add 1. So this reminds me of those memes you see on Facebook a lot. So if I do 5 times 7 times 9 times 11, that's going to be 3,465. And when I add the 1 to that, 3,466. And I'm going to say we can't put 3 into that and not have a remainder. We're going to have some sort of remainder there. This is a common one that gets students. 0 cannot be divided into 0 groups. 0 is empty. So there's nothing to put into a group of 0. Even though you have 0 groups, it's an empty set. And so that's the real issue here when we're trying to deal with 0 divided by 0. Now I have for any whole numbers A and D, I'm going to define that if I'm putting D into A, then D is also going to go into any number times A, which is a multiple. So N times A is just a multiple. So for integers A, B, and D, where D is not 0, if D can go into A and D can go into B, then it can go into the sum of them. If it does not go into B, then it cannot go into the sum of them. If D can go into A and D can go into B, and A is greater than B, then I could do that as the subtraction. But again, if one of them fails it, then the whole thing fails. And the same is true if the first half fails. So if I want to classify each of the following as true or false, and I'm looking at these situations, if 3 can go into X and 3 can go into Y, then 3 can go into the product. That's true from our divisibility properties. If 3 can go into X plus Y, then 3 should also be able to go into X and Y independently. That is going to be false. Remember, that wasn't resulting in the addition, that was the multiplication. If 9 cannot go into A, then 3 cannot go into A. That's going to be false. That doesn't follow any of our rules. Sometimes it might be useful to know if a number is divisible by something just by looking at that number. So we don't want to actually do the division. We just want to say, is it divisible? So for instance, if I've got the number 1,734, if I have a calculator, then it might be easy to know if I could divide it by 17, but especially if I don't have a calculator, it's going to take a while if I try and do that with long division. So what we can do is we can use our divisibility rules. Another method for checking would be to use int divided by on a calculator. A lot of them don't have that at this point, so basically we're using the divisibility rules. But you could actually try and see if it divides, and if I get a whole number with no value behind the decimal, then there would be no remainder. So if you wanted to check it, you could. So these are going to be the rules that you should write down. A whole number is divisible by 2 if and only if the units digit is divisible by 2. That means the ones place. So if the ones place is divisible by 2, the whole number is divisible by 2. Something is divisible by 5 if and only if its units digit is divisible by 5. So that's the ones place. So the ones place would have to be a 0 or a 5. It's divisible by 10 if and only if the units digit or the ones place has a 0. It's divisible by 4 if the last two digits, so we're looking at the ones place and the tens place, represent a number divisible by 4. It's divisible by 8 if the last three digits are divisible by 8. So let's look at those. So take a moment, pause the video, make sure you have all of those written down. And let's look at 97,128, and we're going to look and see if it's divisible by 2, 4, and 8. So to figure out if it's divisible by 2, I look at the ones place, and I say, is the ones place divisible by 2? The answer is yes, so it's divisible by 2. To find out if it's divisible by 4, I look at the ones and the tens place. That would be 28. Is 28 divisible by 4? Yes. To know if it's divisible by 8, I look at the last three digits, the hundreds, the tens, and the ones, and I figure out, is it divisible by 128? And the answer is yes as well. So here's another example. I'm not going to go through it directly, but this one is divisible by 2. It is not divisible by 4. It is not divisible by 8. And you can see the reasonings on the screen. So there's kind of this hierarchy. If something is divisible by 2, it's also divisible by 4, and it's also divisible by 8. So there's this kind of nested idea. So if we're working out from here, something that's divisible by 8 is always divisible by 4. All of them are. Anything divisible by 4 is also divisible by 2 because it encounters. But see here, I got this outside circle. So there are a handful of numbers that are going to be divisible by 2, but not divisible by 4 because part of the circle lives outside of that nested situation. Now let's look at numbers that are divisible by 3. So if they're divisible by 3, the sum of the digits has to be divisible by 3. If it's divisible by 9, the whole number itself has to be divisible by 9. So let's look at an example. If I wanted to know if 1002 is divisible by 3, I would add the digits. So 1 plus 0 plus 2, 1 plus 0, 0 plus 2. And I say, okay, is that divisible by 3? And then to find 9, I just have to do the division. Is it divisible by 9? And it's not. There's a remainder, there's a decimal behind it. What about this one? Well, I'm going to add my digits and see if 3 is going to be divisible by 18. We know it is. So since it's divisible by 3 by that digit process, the whole number is divisible by 3. To check 9, we just have to do the division. And we find that it does work. So here's a couple of examples of applying this. A store manager has an invoice for 72 calculators. The first and the last digits on the receipt aren't legible, so we can't read them. The manager can only read 67.9. What are the missing digits and what is the cost of each calculator? Well, I know I have 72 of these calculators. I know I'm missing 2 digits in here in the receipt, so I can write those as X and Y at the end. Because 72 calculators are sold, it's going to have to be divisible by 72. So since I know 72 is 8 times 9, I'm going to start looking at, is this number going to be divisible by 8? So I have 79y, and I want to know, is that going to be divisible by 8? Well, if y is 2, the answer would be yes. 792 would be divisible, so that the last number has to be 2. Because the number of the invoice should be divisible by 9, we know that it has to actually divide when I add all those digits up. So x plus 6 plus 7 plus 9 plus 2, or x plus 24 has to be divisible by 9. So x would have to be 3 because 27 is the closest number that's divisible by 9 when you add the digits. So a whole number is divisible by 11 if and only if the sum of the digits in the places of even powers of 10 minus the sum of digits in the places that are odd powers is divisible by 11. So that's tricky, right? An integer is divisible by 6 if and only if the number is divisible by 2 and 3. I like that rule. So how does this actually work? If I want to know if something's divisible by 2, I'm going to look at that and I'm going to say, is the last number divisible by 2? No, it's not. If it's divisible by 3, I have to apply my divisibility rule, and it doesn't work there either. So since it's not divisible by 2 or 3, it's also not going to be divisible by 6. For 5, the units digit has to be a 0 or a 5, and it's not, so it's not divisible. For 8, I'm going to have to look at those last 3 digits and see if they're divisible by 8. 583 is not divisible by 8. And then for 9, I'm going to add up all these digits, and some of those digits is not divisible by 9. For 10, it has to end in a 0, which isn't the case. For 11, this is the situation where I'm looking at odd powers of 10. So this is 10 to the 1, this is 10 to the 3, this is 10 to the 5, this is 10. So you see what I'm seeing here? So I'm looking at odd powers. So 3, 5, 6, 9, 7, 5. Those are the digits that I'm looking at to determine divisibility, and it is. Those digits added together is equal to something that is divisible by 11.